Hey guys, welcome to another exciting C++ algorithms implementation tutorial. In today's tutorial, we'll be looking at some sorting techniques that doesn't require comparison. Now, typically, whenever we do sorting, use the sorting techniques like let's say bubble sort, merge sort, quick sort, or in any of these kinds of sort, what we typically do is in at some stage of the sorting algorithm we compare between the variables. Let's say we have two variables a and b, and if a and b if we compare a and b and we find that a is greater than b, then if we are arranging that array as an ascending array, that means the next element has a greater value than the previous element, so it just typically becomes the array, the ordering of the array elements becomes like this. And if not, then the ordering of the array elements becomes like this. Okay, so this is what our standard sorting procedures do, and whatever they do, they have this one thing common, is that they make these comparisons. Now, due to this, what happens is that no matter how great an implementation of the algorithm we make, as long as we are comparing the elements, we can actually mathematically prove that if an array has n number of elements, then it has to do at least n log n number of comparisons. I mean n into log n number of comparisons to sort the whole thing, regardless of any other steps that involved in doing that algorithm. And our today's goal is to eliminate this comparison so that we can actually achieve an runtime faster than n log n. And if you actually see that these fastest sorting algorithms like merge sort and quick sort and heap sort, they have this time complexity of n log n. But today we are going to look at some algorithms that will sort an array of n elements at a time complexity of order of n, which is much faster. Now there are some constraints, but at the end of the day they're much faster, and such an algorithm is counting sort. So without further delay, let's jump into counting sort and let's see how we can sort an array without doing any kind of comparison. Okay, so let me make a quickly make a file. So let's make just a folder here. I don't know why I named it like that, CRT. It doesn't really make sense, but let's just do it. And let's create a file called counting sort.cpp. Now the first things first, let me include something. So hash include iostring, and for random values let's just include a rand, not rand, but to use rand we need a cstdlib. Okay. Now using namespace std and int min. Okay, now let's say we have an array of 10 elements. Just let's quickly initialize an array. First of all, we want every element to be 0, so let's say array 10 equals to 0. What using this kind of initializer list does is it sets all the values of the array to be 0. Okay, this is a quick trick to set all the values of a newly created array to 0, or any old array, doesn't really matter. And let's just set some random values to this array variable. So int I equals to 0, I is less than 10, I plus plus, and we just simply say array I has some random value. Okay, that's it. Now this will be array nd, not array md, but you get it. So now we can just simply see out these values. So array I, and after that we will give a space here. Okay, that's it. And we can just save this, and we can try to compile and run this. So I am using Microsoft Visual Studio compiler, but you can use any kind of C++ compiler. I think every one of those compilers will work. Now we have some errors, so let me fix it first at line number 8 and line number 10. So at line number 10, 8, obviously we need to give it a type, my bad, so int array. And now if we compile it, we get another error, that is I is not declared at line number 13. So let's just quickly fix this issue. Okay, and I think that we need this loop here that I forgot. For some reason I am not coding so well today, but it happens. Okay, so let's first clear our screen. We have a lot of stuff here, and now let's compile and run this, and we can see we have some random values like 41, 128, and 18467 and stuffs like that. Now let's say we don't want that. What we want is we want to sort this value in such a way that we don't have to do any kind of comparison, and for that we need to self-impose a rule, because if we are going to sort it normally, then we need to compare, but we don't want to compare. And our rule here is a simple rule that we know that all the elements of our array has a maximum value, so let's say max val of 100. Okay, all the elements of our array has a maximum value of 100, and no any element will have a value greater than 100. So we can just simply take a modulus of max value when doing the rand, so we can ensure that all the variables in our array has a maximum value of 100. If we run this program now, we can see that this array that we have 41, 67, and this array that we have, it has no element that is greater than 100. So having this constraint, now we can apply count sort on this array to sort this thing. In this case I will be doing it in ascending order, but it's really the same, just you have to do the reverse process if you want the thing to be done descendingly. So let's say counting sort here for convenience, and what we will do is we will count the number of instances of each values that appear in that array. What does that mean? We just simply take an array, array, and we are just going to name it count, so counts counts, and that array will have exactly the all the possible values in that array. Means our count has 10 values, where 0th index represents how many zeros are present in the input array, 1 index represent how many ones are present in the input array, and so on. And first of all, we initialize our whole array to have the value 0 for every element. Now what we do is we simply loop through our array. So I'm just copying this for loop here, okay, because I don't want to type. And then what we will do is we will set increment the counts value, so counts, and we will set the index of the counts as the value of the array, so array I, counts array I. And what we will do is we will increment whatever the value was present. So if count array I was 0, then it will be counts array I will be 1. So let's say the first element is 1, second element is 1, and third element is 1. So counts 1 will now become 3. Okay, so we are just taking the count of the elements that are present in the array. Now depending on the count, we can reconstruct the array without any comparison. So how we will do that? First we will have an index int j, which will be set to the last element of the count. So we will do it in reverse order. Okay, if you do it in forward order, then you will get in a descending order, and if we do it reverse order, then we will get in ascending order. I am doing it in reverse order because I want to get it at ascending order. Now if the array has 10 elements, the last index is 9. So we will set our counts array's index as 9, and then we will simply do a for loop in reverse order. So for int I equals to 9, and while I is greater than or equals to 0, we decrement our I. Okay, It's, I think, quite simple to understand. So we decrement our I. Now what we do while decrementing the performing decrement operation, we first found the last value that's present in the counts array which is not equals to 0. So while counts j is not equals to is not equals to 0, what we will do is we will keep decrementing j. So now we have an index of count which is not equals to 0, and fortunately that is what we will say the value that should be present in the index I of our array. Okay, so not array I equals to array I, but array I equals to counts j, not counts j. Counts j represents the count, but the index represents the value itself, so it will be array I equals to j. And after that we already have consumed one item from our counts array, so we will just say counts j minus minus. Okay, so we will decrement count j. What counts j minus minus means is that we are saying counts j equals to counts j counts j minus 1. It's as simple as that. And now if we run this, if we run this, you will see that we have our array sorted in a very weird way, because we have done some mistakes. So just let me quickly look at it, because I don't usually keep something like a cheat sheet looking at which I am typing, so it sometimes happen. So int max equals to 100, max value equals to 100. So this is the factor. I am setting max value as 100, and then I am doing this kind of thing. So our counts array should contain all the should be able to contain all the values. So counts will have index of this max counts should have at least 100 indexes. Okay, 100 indexes. And this is the first thing that I think the number of the max value, the maximum value, will be the number of the elements, because we need to keep the count of every element. Now what we will do is we are taking the count of every element. So counts array I plus plus, that makes sense. Next what we need to do is we need to set the count to the j, the last element of the counts, and the last index of the counts is 99, and then we do this stuff. So now I think that I have fixed it, and as we can see now, we have something like an contiguous array, which we shouldn't have, because our random function will not produce something like this. So just let me quickly look at it once more, whatever mistake I have done. So while counts j is not equals to 0, we are decrementing j, we are setting array I to j, and then we are setting counts j equals to counts j minus 1. That totally makes sense. So where is the silly mistake that we have done? So int I equals to 0, I is greater than 9, I is greater than equals to 0. This we are printing the array, and we are constructing the array here. So counts array I plus plus, and we are setting the counts to 0, where counts j is, this will be counts j is equals to 0, because as long as the count j value is equals to 0, we are reducing it. Okay, so this was the error. Now if we run this, we can see that effectively we have sorted our array. At the error that we had was that let me just quickly recap it. The error that we had is that this whenever I am saying that this is not equals to 0, but I am saying that whatever the last element that is a non 0 value, stop it there, and stop j at there. and what it will do is it will simply just set it to the last value, because obviously we are not getting 99 as our count, so it doesn't really work that way. But here you can see that it's working quite good. So this is how counting sort is done. Okay, now, and yeah, this is how we typically implement counting sort. Now, here is the question. If we are supposed to sort a larger range of values, let's say if the value is any kind of integer, then what we will do? Do we have to take that many counts? The answer is yes. If you are doing counting sort, then you have to take that many integers. But there is another sorting technique which uses count sort in a limited range and uses it again and again for every radix to sort our array. Okay, so we will look at that sort, and fortunately that sort is known as radix sort. So before we go into jump into radix sort, an advanced version of this algorithm, let me quickly recap what we have done so far. We first took count for every possible value that can be present in the array. Then we go through the array and we take the count of every value in the array. So if there are two ones, then counts 2 becomes 2, so count 1 becomes 2, and so on. And then in the reverse order we traverse through the counts array. Whenever the counts value is a non-zero value, what we do is we take the index of that counts array and we set that index as the value of the array, and then we just decrement the count for that index, and that's it. And this is how you typically do count sort. Okay, so now let's just quit this program and let's create another file called radix sort. So radix dot cp. So now we are in radix sort, and just let me check if I'm recording it correctly. So yeah, we are recording. So now we need to include iOS stream, and we need to include, I think we will include a random and memory, because we need a larger value for our counts array, and unfortunately int max is quite a big value, but it's a 16-bit integer. Okay, int max is a 16-bit integer, it's not an 32-bit integer, which is our main issue here. So we need a better distribution function that can give us that much array. So let's just write some quick boilerplate codes so that we can work with it. So let's say using namespace std int main, and first let's generate our array. So let's say int array. So let's say int size, that is the size of our array, and let's say our array has 20 elements for now. Okay, our array has 20 elements, and let's next create our array. So int array, I am just creating it as a pointer because pointers and arrays are same. If you don't get it, then I have a video in my channel which refers to the relation between arrays and pointers and all the stuffs that are related to pointers, so that it makes the concept of pointers easy to you. But here what I am doing is I am dynamically allocating an array in the heap which will have 20 elements, in size number of elements. Now if I don't explicitly say that this is a constant, then I cannot do this. I cannot just simply write array and then n size. It will not work. It will not work because this is a variable and variables can change, and this is not a constant. So what we can do is we can dynamically allocate an array which will be allocated at runtime. So we can just do it this way. We can create a dynamically allocated array using malloc or memory allocate, and malloc will take the size of the data, so size of int times in size. Okay. So it will give us a chunk of memory worth 10 integers. Okay. Now with that we have it, we can create a distribution function, and using that distribution function we can fill up our array. So just write our distribution here. It looks a little bit strange, but just bear with me. So random underscore device, let's call it div, and then we will say that the kind of range that we are using, the engine that we are using, I are using here AMT1937, which is also a very odd number, and we will call it as a range, RNG for short. And this range will use this device to generate our random number. And if you are wondering how we can generate random numbers in C++ in modern days, this is how we simply generate. And now we need the distribution that we are talking about. So for here I will take a uniform distribution. So uniform. Now if you don't know what distributions are, then you can simply search on Google what distributions are. But distributions are how the ways how the random numbers are present in a set. For instance, there is Poisson distribution, there is uniform distribution and stuffs like that. Now we don't want to get off topic so much, so just keep going on with this. So this TRIBUTION distribution of our this result type. So m this colon result underscore type. Now if you just keep on typing things again and again, it becomes some kind of heavy, so hobby. So you just remember it. Okay, that's how. Otherwise you just whatever ID you are using, it should give you something like intelligence, which will provide you the value. But let's say for example our number lies between 1 and this. Okay, so now what we can say, this all this means is our number strictly lies between this distribution of 1 to this number, and using this distribution we can now generate our array. So we can just simply use our handy for loop. So for int I equals to 0, I is less than n size, which is the size of our array here, I plus plus, and we will simply set, let's say array I equals to distribution over our range. It's like this. Okay, now if that doesn't make you any sense, we can just see out to check what the values that we are getting. So see out and then array I, and then let's say a simple space. Okay, so that we can space separate our array using space. Now we can compile this. So we can say cl radix sort.cpp, and then we can call this radix sort. And if we run this, we go through a lot of error that says identify whatever it's saying. Let's say undeclared identifier distribution has 2 t's. Okay, so let's open the file quickly. And the thing that I have done that actually happens when you don't have any kind of good intelligence is that you are prone to spelling mistakes. That's why I think intelligence is good. Now we also have I declaration, I not declared at line number 19. What we have done previously, I think we have done again, that we forgot to look through and just use the index. So now I guess our algorithm should be satisfied and show us our result. And as you can see that the numbers we have here are between 0 and 99999, and that's what the distribution does. So for example, let's say we want our all the numbers that we have between 1 and 10. Okay, between 1 and 10. And what it will simply do is it will have all our numbers between 1 and 10 inclusively. So if you see that array now, it is one between 1 and 10, nothing else. So just let's forget about that, and let's focus on the actual reason I am using this instead of rand. Is I want to use a very big number, like let's say ff, and this is the largest 32-bit integer that you can represent. I have written this in hexadecimal form because I don't want to remember the numbers. All that matters is all of every character here, uh, like this one, this ff, it should take 1 byte of data to represent, because this is ff means 256 255. So 0 to 255 is 256. So this is effectively 1 byte, this is effectively the second byte, this is effectively the third byte, and this is effectively the fourth byte. And we will also use the bytes to rearrange the data. So now if we quickly save this, and if we just have a look at what our range is, then we can see that this large thing is our range. Okay, this large thing is our range, and these minus signs, they are here because there is a reason of that, is because this is effectively a negative number, because the first bit of the value should always be 0 for a positive integer. So if you are sorting all the positive integers here, we need the first bit to be 0. So we will just reduce one value from it, so it will be ffe, let's say. Now we should have a random distribution of all integers, sorry, of all integers possible which are not negative, and for some reason, I don't know why, they have selected today to have all our numbers as negative. It happens sometime, and I just simply want to remove this e from this earth. So if we just now I think it should work. Yeah, so we have very large positive integers, and what actually I think the problem with e is if we represent e as binary, it becomes 1101, no, 1110, I think. Okay, which also has the first bit as 1. Okay, and we need the first bit to be 0 to have the integer, the value as a positive integer. Now if it was an unsigned integer, then if was fine, but in this case it's not fine. If I would have used something like if let's say 8 or something like, not 8 but 7, up to 7, if I used this till this number, I will get a positive integer. I am sure of it. Okay, I will get a positive integer, but this is a very high value of integer, as you have seen. Now we can simply look at how our radix sort works. Okay, so let's not dive into it, dive into this kind of random distributions and stuff like that. If you are interested in it, then I can surely make a video on how these different kinds of distributions can be implemented on in C, or actually the mathematics behind these kind of distributions. Actually, we can do it, but for now let's concentrate on the radix sort. So what we will do is we will do the radix sort like this. So let's just first let me make some logic on how our radix sort work, then we will implement our radix sort. So the idea behind it is that, let's say we have some value like this, a, and then we have something like b. Okay, and the idea is that we let's say we have this a, we can partition our variable in these groups, because these are binary numbers. Like we have something like this. We have a number that is present in the memory is something like this. Now we can partition this value into smaller indexes like this. Okay, this would be a good example actually. Then AABB. Okay, so we have something like this, let's say. So we can partition these values as using a smaller index. Let's keep it like this. Okay, let's keep it like this. So we then we will sort these numbers depending on the we will sort these numbers one step by one step. So first we will sort this on only this part. Okay, this let's say only using this part. We sort this number using this part, and after we have sorted using this part, these three are same, so the order remains the same. But then we try to sort this number using this part. Okay, we try to sort this number using this part. So what happens is that this value is greater than this value. So what it will effectively do is it will paste it above here, because this value is sorry, my mistake. We are doing it from small to bigger. So this is the biggest value now, depending on this line. So what we will do is we will transfer it at the end. Now we sort it using this portion. Sorry. Now we sort it using this portion, and here we can see this is the largest value, so we put it at the below. So this is how radix sort works. We sort through each radix. For an example, taking a common example, let's say we have 12, 123, and let's have some values here. Okay, to explain. Okay, so first we sort using these first place numbers. So after sorting, this becomes 2 to 1, because 1 is at the end, then 1 to 2, then 1 to 3, and finally 2 3. Okay, because we sort the first decimal place. Now on this using the second decimal place, if we sort, then all of these has 2 as a second decimal place, so it doesn't really matter. Then we go to the third decimal place, and this number, it has 0 as the third decimal place, so it comes first, because we don't write 0 usually, so 23 comes first. Then the numbers that have 1 as first decimal place, that is 1 to 2, and then 1 to 3, and then comes 2 to 1, like this. Okay, but we are using a computer can read binary, so we will rather sort using each byte. Now every byte is of size 8. Okay, every byte has 8 bits, makes a byte. 8 bits makes 1 byte. So what we were going to do is we were going to do 4 sorting, 4 times sorting to do to sort all the bytes. Okay, and for each sorting we are going to use counting sort that we have just learned. Okay, so let's just say that we have our radix sort here, and it takes our array, so int pointer to our array, int star array, and it also takes the number of elements, so n elements, elements. Okay, so what we will do is, and we need a temporary array to keep the unsort the intermediate step arrays, so I will just call it temp array, and it will be of the same size of our array. So just let me quickly create another dynamically allocated array of which has the size of n elements, so size of int times n elements. Okay, so this is a temporary array. Now what we will do is we will go through each byte. So for int I equals to 0, and regardless of whether you are using a 32-bit architecture or 64-bit architecture or whatever integer you are available, we can just say I is less than size of int. So for every byte we will do one iteration, because size of returns how many bytes are present in that variable, and then we just simply say I plus plus. And here what we will do is we will apply counting sort. So let's say counting sort, and we will count sort the array, store the result to temp array. Okay, store the result at temp array, and what we will do, and let's pass the number of elements. So these many elements will be sorted, and finally we want to know, to inform our counting sort, which index to be seen, or which byte we are using for the counting sort. Okay, and after that is done, we can swap our array with our temporary array. I am going to do something that will work here, but never do it, because it's something that only should be used, cpy mem copy, which only should be used if it's a string. But here actually we are swapping the whole memory, so I think it will work faster. But this is something that you shouldn't use to copy one array to another array. I'm just exactly copying the whole data, so I'm doing this, but this is not how you do it. Okay, just to not write another for loop, size of it. So what we did is we take this amount of memory of temp array, and then we put that memory at array. So effectively we copy temp array to array. Okay, but don't use mem copy for anything other than a character string. Now characters can be considered as bytes, so I know that I am copying the bytes in right order, but don't do this. This is not the recommended way of copying integers, okay, from one array to another. But this works. This mem copy works for this also, but mem copy is strictly for copying strings. Now that we have done it, we can just simply once again produce our great count sort. We will modify the count sort a little bit so that we can do it using that array. But so un counting, so counting sort, we can do it using the bytes, and we can store the values at temp array rather than modifying the array. So that will be the change. So let's first create our signature. So we have this array, which is an integer list, and we have output array where our temp array resets. So out array, let's call it out array, and then we have our elements. So int n elements, and then we have our what number of bytes we should mask. So I will call it mask byte, mask byte. So which byte to be masked? Now you can just simply take a modulus if you want to do it using 10th decimal place. It doesn't really matter. I'm just doing it using bytes because I want only to do the minimum number of counting sort, which is 4 here. And I can just simply define a macro here called byte mask, which will effectively mask a byte. So byt byte mask, and I can set this value to something like 0xff, which is 1 byte. Okay, I just told you earlier. Now I can also define the size of our counting sort array, because this kind of information works. So byte size, like how many bits are there in a byte. So byte size, which is also 0xff. Okay, so we have these are byte mask and byte size. So obviously we will have, first of all we will have our mask ready that we want to use. So we will have our int mask, and before we prepare the mask we need to know how many bytes we need to offset it. So int byte offset is equals to, every byte has 8 bits, so 8 times mask byte. So what happens when mask byte value is 0, that the first iteration, then our byte offset will be 0. When max byte value is 1, our byte offset will be 8, so we will skip the first 8 bytes. Then when our max byte is 2, our byte offset will be 16, so we will skip first 18 bits and so on. Okay, this actually should be bit offset, but let's just go with this name here. Okay, but all it does is it skips that many bits, and then we prepare our mask. So how we prepare our mask? We prepare our mask like this: byte mask. Okay, and not byte mask, yes, this byte mask, this mask, and this mask you can see is it's 255, so it's at 0. Now this actually represents something like this: 1 1 1 1 1 1 1. Okay, 8 ones. I don't know if there are 8 ones, but this effectively represents 8 ones. So what we can do, uh, and let's understand how it will work. So let's say our byte mask is this 1111, and we have a value like 1010, then we have 1111. This is our another value. This is just a logical space. Okay, so whenever we are doing the 1101, so when we need the first byte of this value, what we will do is we will perform an bitwise AND operation with this byte mask, with this byte mask. Okay, with this byte mask, with this portion, and it will give us 1101, which is at that position. Now when we perform it with the second portion, with this portion, it will give us what? It will give us it will give us 1010, because if we AND 0 with 1, we will get 0, and if we AND 1 with 1, we will get 1. If you don't understand what bitwise AND and stuffs like this these are, then you can ask me in the video chat, and if there are some comments that want to see these kind of things in explains in detail. These are actually very elementary things if you are studying computer science, and this video particular targets to a little bit mature programmers. So if you don't know these kinds of thing, you can ask me and I will make a video of it. But simply what we will do is, we know how many bits that we have to shift, so we will just shift our byte mask that many bits. Okay, so byte offset, nothing else. And there is that one problem that we had, if you remember, is that the first bit is the sign bit, and we have to take care of it. So what we will do is, we will check if mask byte is equals to something like a 3. If the mask byte value is 3, which means if we had 0 1 2 3, if we are targeting the fourth byte, the final byte, taking that rather than 3, it should be like size of int. Okay, this is far more accurate. If -1, okay, then if it's 3, because in my operating system, size of int is the 32 bit, so it should be 3. If that's so, what we will do is, we will just say mask byte and equals to, and we will just AND the last bit, and we will unset that bit. I mean, we will convert the last bit as 0, from 1 to 0. So to do that, we need a number that is something that looks like something like this. Okay, so the last number should be this. So how we will achieve that? We will take AND 1, and then we will shift it to the last, and then what we will do is, we will invert it. So 1 will become 0, and all other zeros will become 1. So how we will do that? So first things first, we will take 1, okay, which we will take as an unsigned long integer, and then we will shift it by size of int times 8. Okay, because this will give us the number of bits that we want to shift, because we are doing some bitwise operations. And finally, what we will do is, we will make the whole thing inverted. Okay, so that's done. We have our mask. Now we need our count array. So we say long counts, count array. That's a count array, and it will have 0 to 255, so 256 bits. and to hold 255 I need one more cell to our count array. So byte size plus 1. Okay, because otherwise if I have 255 here, then it can store up to 250 0 to 254. So if I have to save 255, then I have to give here 256. That is byte size plus 1, and we will initialize to 0, this to 0. Okay, so we are using an initialize list here. We can also use for this kind these for these mallocs, we can use just int array new int, but I am a stupid person. What can we do? For int I equals to 0, I is less than n elements, n elements I plus plus, and we do the step we do the same stuff. We find the index. So let's say the index is v, which is equals to array I, and we effectively take the mask as or, so mask, and this will give us a value between 0 to 256. The value will leave between 0 to 255. Okay, 255. This will be the v will always be from 0 to 255. So we can we can take the measurement of the v using our counts array. Okay, that's a good thing. So now what we will do is we will say, and obviously we need to shift the now this value, you need to shift it to the rightmost part. So we will just perform the reverse operation that we have performed here for the mask. So v equals to v, and that time we had done a left shift, this time we will do a right shift with the exact byte offset, so that our v value is always between 0 to 255. Okay, this is how we get the index of the v. And the next part is simple. We say that count array, and we increment the number of elements for the value that is present there, so that we can take the counts of everything. Now why long here? Because we have a lot of integers to consider, so I just took long so that we don't get any memory leak. I don't know how many integers will be there. Let's say in case of here we are using only here we are using only 20 integers, but if it was something like this, if they were like this, okay, and all the integers were at the same place, actually int will also work, but just let's leave it as well. The only now we have done our counting sort. We are going to reconstruct our array next, which is effectively the end of this algorithm. And here we will do something that is actually a little bit different from counting sort, and we will we are going to do it. There are two reasons. First of all, we are dealing with our we don't want to lose the values of our array, so we are storing it to another array, out array. And secondly, the values of the arrays and the values at count are different. So what we will do is we will offset our counts. So how we will do that? It's actually very simple. Let me show you. So first things first, for int I equals to 0, I is less than or equals to byte size I plus plus. So we look through all the variables that are present in the array, and we increment the ith array. This should be 1. Okay, why I am just telling you a moment, this should be 1, and we increment it by the last count array data. So I minus 1. So let's take a simple example. Our count array had 2 zeros, no ones, and 3. So our count array index was suppose 0. This is our index 0, 1, 2, 3, and 4, and our array was something like this. Let's say, okay, we had 2 zeros, 2 3 2 twos, 3 twos, and 1 4. So this count array, we are now going to convert it like this. We have two zeros, then one would have 2 plus this value added, so one would start at 2. Okay, now one had no value, so this will be the same. Now for 2, this last value will be added, so for 2 it will become 5, and for 3 it will become 0. It will also be 5 because we are adding the last value, and for 4 it will become 5 plus 1, so it will become 6. Okay, what's the benefit is that for 4, let's say we are at 4 here. Okay, we are at 4. If we check here, how many elements does our array have? 3 plus 2 plus 1, we have 6 elements in our array. Okay, so the 4 is going to be our sixth element. Okay, we are sure that 4 is our sixth element. Okay, now we decrement 4 by 1, so 4 becomes 5. We decrement 4 by 1, so 4 becomes 5. And then we check for the third row. Okay, it's the same, so we don't do anything. Then we come here and we decrease this 3 times. We are obviously decreasing using count, so 3 becomes 2, and then this 5, so this 4 has been used, so this count will be set to 0. Okay, and I am doing something crazy here. Okay, so this is 5. So now the array is like this, and this 3, we will take one value from here, so this will become 2, and this 5 will now be decremented also, so this 5 will become 4, and we have a 2 here. And similarly we'll have or two twos more, and so this 4 will be decremented to 2, and then 3, and then 3, and then 2, and now this 2 is same to 2, so and this will be 0 because we have used all the 2's. So last we have three twos, and then we have this 2 zeros. Okay, so these 2 will become first 1 and then 0, and that is effectively we will use all the zeros here, and then we will have our zeros here. Okay, I'm doing it in the reverse order. So we have this array sorted in the reverse order, so 0, 2 and 4. This is how we will perform our counting sort here. A little bit of different implementation. There are two benefits of doing this. First of all, I have shown you the first simple way of doing the counting sort. Now I am showing you a little bit complex way of doing the counting sort. So you have both the things in your arsenal. So let's just sort them using this new counting sort array. So for we are doing the reverse loop, int I equals to elements minus 1, and elements minus 1, I is greater than or equals to 0, I minus minus. Okay, and with my luck we are going to have some errors, and then I will fix that, and ultimately we will get a working solution. I can show it and show it. So int let's first get the index. So let's say count index, and this will be we will get the index from the array element using the mask, the same thing that we have done before. So we will say array I and mask, and then we will make it shift to the byte offset. That is, we are effectively getting the value of v here. Okay, I did it in 2 steps here, but I just wrote it in 1 line here, nothing else. And now that I have the index, what I will say, we'll see that in our out array, we'll have our count array of count index, and effectively that index has to be reduced. So count index, the value at that index should be reduced. So count index minus 1. Why minus 1? Because we are using a zero based indexing. So minus 1, we are using from, actually not zero based, we are using 1 based indexing, because if you look here, then our distribution starts at 1. Okay, our distribution starts at 1. If our distribution starts at 0, we can do different kind of thing, but it doesn't really matter. Okay, the kind of distribution that you are using Depending on that, you will do this, but ultimately what we are doing is we are just setting our out arrays value using our array I. Okay, so we have modified this count array a bit, and depending on that little bit of modified count array, depending on that little bit of modified count array, what we did is we we sorted the out array. Nothing else. Okay, and this time for every iteration we are getting the index from the value of the array. Okay, so know that kind of while loop and tracking the track of the index, this is also a benefit. So we have implemented the counting sort, we have implemented the radix sort. What we can do is we can free the this temp array. You can say free temp array, free the memory here. You can also free the memory here, and you can apply counting, so you can apply radix sort. So you can just simply say radix sort, and then we will say array and in size. Okay, now with my luck it's not going to work. Yeah, uh, count negative or too big undefined behavior, which is at line number 47, and counting sort is not so 17 and 49. Let's say what happened. So at line number 17 what happened is, at line number 7 what did it say actually. Let's just see. Shift negative or too big undefined behavior. Okay, and that is a warning, so we can remove we can so only 49. Okay, only 49, 49, maybe 49. So 49, if you go to 49 we have this counting sort here, and this name is capital counting sort. Okay, so I'll just turn this everything into capital. Let's make it a radix, let's make it counting. Okay, let's make it radix. Okay, function names capitalized, nice way to represent. And we have this, we don't have no idea if it's sorted or not, but I think it's sorted. So we will just take some more samples to do it. Let's just include, let's say if string. Okay, because we want to deal with some larger number of samples, and let's change this n size to a large number. Okay, so let's see something like this. We have this many elements. Now if you're going to use that sorting technique, it will take a little bit more time, but we have our advanced radix sort, which will take order of n time rather than order of n log n, so it should be faster than typical sortings. And we are not going to print all these values here. We just, it will take a lot of time because IO on the console is actually very slow, so we will just create a file and put everything in the file. So web stream web stream, we'll call it file, we'll give it a name like output.txt. This is our file name, which is not so great. And if we will check if our file is not open, so if not file dot is open, is underscore open, then we will return -1 because we were unsuccessful, and obviously we need to free the resources here. Now if the program ends, it actually frees all the resources, it doesn't really matter, but this is a good practice whenever you are working with dynamic memory. And if that's not, we are going to write it into file. So file, let's just call it out. Okay, out stands for output, I think that will be good. So let's call it out. just to keep things a little bit names a little bit good. So output here and output here. Then we will write our value of array I here, and after we have written our value, what we will do is we will put next line character backslash n here, and this is a character, so I think I should do it like this. It doesn't really matter, but I'm a stupid person, so I do this kind of stupid things. And if it's successful, then it returns 0. Nowadays you don't need to return 0, but still whatever. And after I have written it, I will close the file. So output dot close. Now hopefully this will crash because of my stupid luck, but if it doesn't crash, we will have a file. Okay, it crashed, and we did the same mistake again because we never learn. Actually you learn, but I never learn. Is that I need to put this loop and then output use the index. Okay, without this loop this index doesn't work. So now if we run this with that many number of time numbers, it should take a little time to sort, or just my program is my computer is running on fumes, I don't know. And does it take this much time? Yeah, it does. So let's let it do its job first. Actually most of the time I think is wasted on writing the file, because writing on file is very slow in comparison with doing arithmetic operations. But if our program has run correctly, then we have something like our output.txt. If we read it, okay, the file is big. We can see that all the values that we had are sorted. Okay, we can see that these values are sorted. Okay, if we jump to the last value and see that this is the last value, and every value is sorted. Now how many numbers we have sorted here? We have sorted around 1 2 3 4 5. So this is 6, this is 1. We have sorted around 10 million numbers. Okay, so we have done sorting 10 millions number in less than a minute, because my PC is not that powerful, but we have sorted 10 millions number in less than a minute using our uh, what it says, using our radix sort. Okay, and the numbers, some of the numbers were really big, and we did it using radix sort. So I will be giving a GitHub link in the description of the video, so that you can look into this algorithms. And I think that's it for today. I hope you have learned something new, a way of sorting integers without counting, without comparison. And both these algorithms are of order of n. Okay, both these algorithms are of order of n. And what we did, just let me recap for once more for you guys, is we applied counting sort on every byte of the data, and doing that we performed radix sort by sorting every byte of the data. Now one thing that I think I should mention is that, let's say we have two numbers like this. Let's say 1 1, let's say 1 2, one number is 1 2 and one number is 1 3, and one number is 1 4. Okay, let's say this is what we had, not this one, let's say 1 2 1 3 1 4, Well, I'm not writing this. The main thing is that you can look up into the net, and you can use any kind of sorting technique in this radix sort, uh, not only counting sort. But the only thing is that the sorting technique must be stable. Now what does stable means? Stable means is that if two values, suppose let's say 1 and 1, this is the first one and this is the second one, are in order, in a order. Okay, so this is the first one, let's say this is the first one and this is the second one, in order. Then after sorting those values, after sorting that array, let's say we have here 3 and here we have 4. Okay, 3 and 4. So after sorting, it should be like this one, and this one should be the first one in the first array, this one should be the second one in the second array, this 3 and this 4. Okay, this should be the sorted result. Now if the sorted result is like this order of the elements in the same with the same value is maintained after sorting, then this kind of sorting is said as stable sort. And some stable sorts are counting sort, which we can use. Okay, we can also use insertion sort, which is also sorting sort, counting, so counting sort. We can use insertion sort, and we can use bubble sort, and we can use merge sort. These sorts, these are stable sorts, they do the sorting like this. But if we use something like a quick sort, which is not a stable sort, our radix sort will fail, because why it will fail is because we are sorting a part, but the remaining sorted results should be same. So the result of the first sorting should not be affected. I mean, this sorting in the loop should not be affected by the second or the third sorting. So you need to remember this. You can replace this count sort with any kind of sort, given that that sort is a stable sort. If you don't understand stable sort, just Google it. You will get a lot of reference materials to understand what a stable sort is. Counting sort is one kind of stable sort. Okay, so I think that's it for today, guys. I hope you have enjoyed this video and learned something new. So please leave a like or share this video with your friends. That helps me a lot and motivates me to make these kinds of video. So that's it for today, guys. Thank you very much.